What if I told you there was a chip that could run AI 4 times faster than Nvidia's best GPU at 1/5 the cost, using only 1/3 of the power? And what if I told you that chip was so good, so threatening to Nvidia's dominance, that Jensen Huang had no choice but to spend $20 billion to make it disappear? In the last episode, we covered the shocking Christmas deal that sent shockwaves through Silicon Valley. Today, we're diving into the technology that made Nvidia panic. This is the story of the chip that beat Nvidia. Welcome back to our deep dive into Nvidia's $20 billion Christmas gamble. If you haven't watched episode 1, go check that out first, because we laid out how this deal went down and why the numbers were absolutely insane. But today is about the why. Why would Nvidia pay triple valuation for a startup? Why did they move so aggressively? Why was this particular company such an existential threat? The answer lies in understanding two things: the shift happening in the AI industry right now, and the revolutionary technology Groq built to take advantage of that shift. By the end of this video, you'll understand why Nvidia had no choice but to eliminate this competitor, and why the future of AI isn't just about being smart anymore, it's about being instant. Let's start with the big picture. For the last 3 years, if you wanted to talk about AI hardware, you were talking about one thing: training. Training is the process of building an AI model. It's when you take billions of data points and teach a neural network to recognize patterns, generate text, or create images. This is how GPT-4 was made. This is how Claude and Gemini and every other large language model came to be. And training requires absolutely massive computational power. We're talking about thousands of chips running for weeks or months at a time, crunching through unfathomable amounts of data. Nvidia owned this market completely. Their H100 and Blackwell GPUs became the gold standard. If you were serious about building AI, you bought Nvidia chips. There was no real alternative. Sure, Google had their TPUs, but those were mostly internal. For everyone else, it was Nvidia or nothing. Jensen Huang basically had a monopoly on the shovels in the AI gold rush, and he made a fortune from it. But here's the thing: the market is shifting, and this shift is what kept Jensen up at night. Because once you've trained a model, once GPT-4 or Claude exists, what matters next? Using it, and that's called inference. Inference is when an AI model actually answers your question in real time. You type a prompt into ChatGPT, the model processes it and generates a response. That's inference. You ask your voice assistant a question. Inference. A self-driving car makes a split-second decision to brake. Inference. And in 2025, for the first time ever, global revenue from inference surpassed revenue from training. The market flipped. Think about it. How many GPT models does OpenAI need to train? A handful. But how many inference requests do they process? Billions, every single day. From millions of users asking questions, generating content, solving problems. The future of AI isn't building more models. It's running the ones we have, faster and cheaper and more efficiently, billions of times per day. And this is where Nvidia had a massive problem. Nvidia's GPUs are incredible machines. They're powerful, versatile, and proven. But here's the dirty secret: they weren't designed for inference. GPUs were originally built for graphics rendering, video games, movie special effects. Then they got repurposed for AI training because their parallel processing architecture happened to work really well for crunching massive datasets. But inference is a different beast. Inference needs speed, low latency, instant responses. When you ask ChatGPT a question, you don't want to wait 5 seconds for an answer. You want it now. And Nvidia's GPUs, for all their power, have inherent bottlenecks when it comes to speed. The main culprit is memory architecture. Nvidia chips use something called high bandwidth memory, or HBM. It's incredibly fast compared to regular computer memory, but there's still a physical distance between where the computation happens and where the memory is stored. Every time data needs to move from memory to the processing cores and back, it takes time, microseconds, sure, but in the world of AI inference where you're processing billions of requests, those microseconds add up. They create latency. They slow things down. For training, this isn't a huge deal. You're running a process for weeks anyway. What's a few microseconds here and there? But for inference, for real-time applications like autonomous vehicles making split-second decisions, or voice assistants that need to feel natural and responsive, or robotaxis calculating the safest route in milliseconds. That latency is the difference between life and death, between a product that feels magical and one that feels clunky. Nvidia knew this. They knew their GPUs weren't optimized for the inference-first future. They were building new chips, trying to iterate, but it takes years to redesign fundamental architecture. And then Groq showed up with a chip that solved the problem in a completely different way. Enter the language processing unit, the LPU. While Nvidia was trying to make their GPUs faster for inference, Groq took a radically different approach. They asked a simple question: what if we designed a chip from scratch specifically for inference and nothing else? No training, no graphics, just raw, blazing fast inference. The result was architectural genius. Instead of using high bandwidth memory like Nvidia's GPUs, Groq's LPU uses on-chip SRAM, static random access memory, the same stuff used in CPU caches. Why does this matter? Because SRAM sits directly on the chip. There's no distance to travel, no bottleneck. When the processor needs data, it's right there. Instant access. But here's the trade-off. SRAM is expensive and takes up a lot of physical space on a chip. You can't fit as much of it compared to HBM. So Groq made a calculated bet. They optimized for speed and deterministic computing, sacrificing some flexibility. While a GPU is like a massive factory that can manufacture many different products, an LPU is like a railgun. It does one thing, and it does it better than anything else on the planet. The results speak for themselves. Groq's LPU was clocked at 4 times faster than Nvidia's top GPUs for inference tasks. 4 times. That's not an incremental improvement, that's a generational leap. And it gets better. Because Groq eliminated the memory bottleneck and optimized specifically for inference, they achieved this speed at 1/5 the cost and 1/3 the power consumption. Let me say that again. 4 times faster, 5 times cheaper, 3 times more energy efficient. For data centers running millions of inference requests per second, this is transformational. Your electricity bill drops, your hardware costs plummet, your response times become imperceptibly fast. And for applications where latency really matters, this was game-changing. Autonomous vehicles could make decisions faster. Voice assistants could feel truly conversational. Real-time AI applications that were previously too slow suddenly became possible. Groq didn't just build a better chip, they built a paradigm shift. Now you might be thinking, okay, Groq has a faster chip, but Nvidia is huge. Can't they just build their own version? Yes, eventually. But here's why Groq was an existential threat. First, time. Redesigning chip architecture from the ground up takes years. We're talking 3 to 5 years minimum from concept to production. In the fast-moving AI industry, that's an eternity. Every quarter that Groq had the speed advantage was a quarter where customers could choose them over Nvidia. Second, the ecosystem risk. Nvidia's biggest moat isn't actually their hardware, it's CUDA, their proprietary software platform. CUDA is what makes Nvidia chips easy to program and hard to leave. It's the lock-in that keeps developers in Nvidia's ecosystem. But Groq was building technology that worked around CUDA. They were creating a viable alternative path. And if Groq succeeded, it would prove that you could escape Nvidia's walled garden and actually get better performance doing it. Third, and this is the big one, the pattern. Groq wasn't alone. Google built TPUs to escape Nvidia. Amazon built their own custom chips. Meta is working on their own silicon. Every major tech company is trying to break free from Nvidia's monopoly pricing. Groq represented the democratization of that capability. If a startup could build chips that beat Nvidia on speed and cost, what's stopping dozens of other companies from following the same playbook? Nvidia looked at Groq and saw the first domino. If Groq succeeded and went public, if their technology became widespread, if developers started building on their platform, Nvidia's stranglehold on AI infrastructure would begin to crack. And once it starts cracking, it's hard to stop. The inference market is projected to be worth hundreds of billions of dollars over the next decade. Nvidia needed to own it, not share it, own it. So they made a decision. Instead of competing on technology, which would take years and might not even work, they would compete on capital. They would simply buy Groq, absorb the technology, hire the engineers, and integrate the LPU architecture into Nvidia's product line. $20 billion to eliminate an existential threat and secure the entire AI stack from training to inference? From Jensen Huang's perspective, that's not expensive, that's insurance. Here's what makes this story so important. It's not just about one deal, it's about what this deal represents. Groq proved that you could out-innovate Nvidia. They proved that with smart engineering and focused architecture, a startup could build something genuinely better than what the trillion-dollar monopoly was offering. And Nvidia's response wasn't to compete, it was to acquire. This is the new playbook in AI. When a threat emerges, you don't fight it, you buy it. You absorb the innovation, hire the talent, and maintain your dominance. Microsoft did it with key OpenAI partnerships. Google does it constantly. Amazon too. And now Nvidia just executed the most aggressive version of this strategy we've ever seen. The message to every AI hardware startup is clear. Innovate all you want, but if you threaten the giants, you'll either be acquired or crushed. There is no third option, and that should concern anyone who cares about innovation and competition. Because when the fastest path to success is getting bought by a monopoly, what happens to the scrappy entrepreneurs who want to build independent companies? What happens to the breakthrough ideas that need a decade to mature? They disappear, just like Groq. So that's the story of the chip that beat Nvidia. A revolutionary architecture that was faster, cheaper, and more efficient than anything the market leader had. A technology that represented a genuine threat to Nvidia's dominance in the next era of AI. And Jensen Huang looked at that threat and wrote a $20 billion check to make it go away. The LPU technology isn't dead. Nvidia will integrate it into their product line, but it will be on Nvidia's terms, at Nvidia's prices, within Nvidia's ecosystem. The competition is over, the consolidation is complete. In the next episode, we're going deep on the man behind Groq, Jonathan Ross, the ex-Google engineer who built the TPU and then built Nvidia's worst nightmare. We'll explore why Nvidia didn't just want his technology, they wanted him. If you're enjoying this series, hit subscribe and drop a comment. Do you think Nvidia's move was brilliant strategy or dangerous monopoly behavior? Let me know your take. And if you missed episode 1 on how this deal went down, I'll link it in the description. This is a story you don't want to miss any part of. Thanks for watching.